Okay, so let's go ahead and get started here. Hello and welcome to my webinar today on predicting airflows as you design. My name is Sashi Sitambaram, and I'm coming to you live from very snowy Rochester. So I hope everyone out there is staying warm and safe in this weather. So for today's webinar, we're going to be looking at um, a system that moves air. So basically, if you have a fan or say a set of blades, a turbine that is moving air from one location to another location. So for example, some form of a cooling system, or perhaps if you are designing, if one of your applications has air that's rotating, and you're building a type of fan or blade that's rotating that air, you'll find this webinar to be useful. So all these concepts that we're going to be talking about today can also be applied in a liquid form as well. So for this webinar and this example, we're going to be talking about air, but in computational fluid dynamics, it's the concept of fluid and gas is very similar. So if you are dealing with a water cooling system or a system that moves water from one location to another using some form of like a blade or fan type of application, a lot of this is applicable as well. So again, as I had mentioned, for this webinar, we are going to be focusing on designing a fan. And as you're designing something like this, typically a few keywords come to mind, right? For one is rotation. How fast is this fan or this set of blades moving? So you have to typically set some rotation to that. Using some of our techniques today, you'll be able to see how we can change that rotation, or how you can basically set that rotation. So some form of RPM or radians per second. Velocity, right? So once you have this air flowing through the fan, what type of velocity is the air at? Obviously, with velocity comes some form of pressure as well. So if the air is moving faster or moving slower, there might be a different pressure, dynamic pressure building up in your system. Blade angle. So this is something that I've seen in recent times in a few of my customers' applications where they're changing blade angles in your fan to create a more uniform flow. Airflows. So perhaps if you want to create a CFM value chart. So a lot of times if you buy a fan, it comes with these values. So it'll typically be CFM versus air pressure. So we're going to take a look today of how we can put together this chart ourselves. So in most application, if you're buying a fan and you're trying to replicate that and maybe modify it for your own purposes, you don't have these charts until you build a physical prototype, and then you calculate the velocity and calculate the air pressure and create the charts yourself. Now, by running this virtually in our simulation flow package analysis, you'll be able to reduce the cost of prototyping. So you probably will not remove physical prototyping altogether, but you can perhaps cut down the number of prototypes you will use, and also save you some time because now you're no longer designing in a black box. So you actually have an idea of what to expect as you create the physical prototype. And of course, just relating back to rotation, typically you want to set some RPMs and you want to change the RPM just to see how it affects your system. So for today's analysis, we're going to take a look at this very complex fan, um, and it's going to be rotating. The fan is going to spin at 10,000 RPM. That's the criteria that we've set, and it is spinning at room temperature, so just right about 70 Fahrenheit. We are trying to find the airflow velocity, the air pressure from the airflow velocity, and of course then create some airflow curves or chart based on those values. So now when we have this in physical prototype, this is typically not that difficult to find. You can use some form of air calibration and extract that value. However, if you are in the business of customizing these types of blades or building these types of blades, typically you will fall under some form of standard, so ANSI standard or AMCA standard, that you need to test these blades on. So that's really what we're going to focus this example around. You've designed this fan blade, but now you need to know whether it's up to standard. So typically when you're dealing with fan standard test setup, it will look something like this. So this is one of maybe 4 or 5 the fan standard test setup that is provided to you by ANSI or the AMCA 210 standard. So just let's kind of go over this setup real quick, just to give you a better understanding of what we're looking at. So this is where your fan that you're designing will reside. It will sit right here. This is a nozzle where the air is being sucked in. As the air flows through your system, typically there might be some turbulence. The air might be non-uniform, and that is the purpose of this cell straightener right here. What this does, it will straighten the air out, and as it flows to your outlet, typically you would have a pitot tube right here, and the purpose of this pitot tube is to ensure that you're meeting the right gauge pressure requirement. So this air will not just blow out into atmosphere. So you would have this throttling device located at the outlet, and typically a throttling device in real world, what I've seen is they might use like a sphere, so something like a bowling ball, or something that looks like a bowling ball at least, that moves in and out of the inlet. So it doesn't completely close it, so it allows for some air to flow out, but what that does is it increases the gauge pressure or the pressure buildup in the system. And you will see that as this throttling device moves back and forth, the pressure, the air pressure, and the velocity changes as well. So the pitot tube right here allows you to ensure that your throttling device is in the right location. So in this standards, the ANSI AMCA 210 standards, they will give you that the P load of the pitot tube. So it will either be 1,000 PA or 2,000 PA, whatever it is. You have to test your system or your system requirements based on that. So in reference to your having your this pitot tube right here and calculating the pressure in the system, that was the whole reason why I put this chart in here. So in real world, your pitot tube will be attached to some gauge calibration or a device that shows you what the pressure is in the system. This pressure is typically shown to you, given to you as P gauge, so gauge pressure. So 1,000 or 2,000, that's gauge pressure. So that is additional to the atmospheric pressure. SolidWorks simulation, and this is pretty standard with most computational fluid dynamic softwares in the market. It does not actually allow you to simply set a pressure gauge. It will give you two options, whether to just set it as atmosphere or set it as an absolute pressure. So basically, if you have 1000 Pascal is for your what your standard is supposed to set to, you take your P atmosphere, so that's typically 101 325 Pascal, and add 1000 Pascal to that, which will give you the P absolute, and that's the value that you will set within the analysis to meet that that pressure gauge. So this will make more sense when we look at the model, which is what we're going to jump into right now. So let's switch to SolidWorks. So here is the model that I have put together based on that standard, which I think meets all the requirements that we look at. So as long as you have this this setup right here, you'd be able to extract all the values that you need to match that physical prototype testing. So let's take a look closer here at this system. So if you recall the table fan that we were looking at, so this table fan right here, you actually don't need the entire fan. All you really need is the blade. So we extracted the blade and we put that into our physical test setup here. So you can see that how my blade sits in that location. This front nozzle represents where the air is being sucked in to the fan. So in this case, I'm actually going to be able to control how the air is being pulled into the system. Then I have my straightener right here, and in this analysis you're going to actually be able to see how that air is turning uniform as it passes through the straightener. So it actually does take into account the physical properties of your entire system. It's not just fluid and gas. And what I have here, this is what I call a dummy plate. So named it dummy plate, and this plate right here actually does not exist in the analysis. That plate right there is an invisible plate that is placed to extract results. So all my results for this analysis is going to be based on this location. So this location is also provided to you through that standard. It's where you have to extract or gather the velocity results and the pressure results as well. So this will be typically some x value, x distance value from the pitot tube. So this doesn't really matter where it is here in the analysis, but as long as you are on the right distance from the pitot tube, you should be fine. And what we're looking at here, this is our outlet. And for this analysis, we actually don't need to have a throttling device, or we don't actually need to have like a sphere there to control the pressure. Why? Well, the reason is because in the analysis, we can set what the pressure is as it comes out. So if it's not atmospheric pressure and it's higher than atmospheric pressure, then I'll just set it at a higher pressure as it comes out, and you'll be able to see how the velocity changes. Okay? So let's go ahead and take a look at how we can put this analysis together. So as you can see here, I've actually turned on my flow simulation add-in. If you look under the SolidWorks add-in, SolidWorks flow simulation is indented, which means it's turned on. That brings up the flow simulation tab. And what I'm going to do is I'm going to use this wizard tool right here to walk me through setting up all my initial conditions for this analysis. So I'll set that up and I'll call this live test. I'll hit next. So for my units, obviously I can pick some predefined units for this analysis. So in this case, I'll probably pick IPS. However, there's a few parameters that I want to change just based on how I'm gathering the results and how I'm going to be analyzing the results. So for pressure and stress, I'm going to actually change this to Pascal. For the velocity, I'm actually going to just leave it inches per second. And for temperature, I'll say Fahrenheit. That's good. And I'll hit next year. And this is where we specify what type of analysis we're looking at. So obviously, this flow simulation has a number of analysis that you can run. So I'll show you later what are the modules that come with this computational fluid dynamics package. But for this instance, what I'm going to do is I'm going to use an internal analysis. So I don't actually need to consider external, because all my air is being controlled within an internal system. As I had mentioned, I created this nozzle right here, and all the air is going to be sucked in from this nozzle. So I actually can represent the inner faces of this nozzle as atmospheric pressure, or atmosphere, atmosphere temperature and pressure. All right, so in this analysis, I actually won't be considering any type of temperature gradient, so heat conduction in solids is not applicable. There's no radiation. This is a steady state analysis, so basically I'm just going to turn the fan on. I'm going to let the air flow, and once everything has reached steady state, we'll gather the result. So it is not a transient analysis or time dependent, so I won't be checking that. I will take into account gravity, because the direction of the airflow is a concern to me, right? I mean, it's flowing in the x direction, but gravity is in the y direction. So I want to be sure that it's taking into account the acceleration of gravity when I collect my velocity results at the back end. And of course, I do have a rotating component in here, so I'm going to check rotation. And under rotation, you do have three types. You have a local region averaging, sliding, and a global rotation. So global rotation is when your entire system is moving or rotating, which is not the case here. I only have my fan is rotating, and in turn it's rotating the air. So that leaves us with local region and averaging and sliding. So the local region sliding is typically used when you have a time-dependent analysis. So this actually takes into account the change in time, as well as it will take into account the pressure that's affecting your system as it rotates. So this, what we call a sliding mesh, the mesh changes as the part is solving or rotating. It does take a little bit extra time to solve. So in this case, we are going to just use local region averaging, which seems to give pretty good results. It averages how it rotates, and it's based on the geometric shape of the blades, and we've gotten very good results in terms of how the air comes out of the blade rotating, any type of turbulent flow or non-uniform, and how it turns uniform through that straightener. I'll hit next here. So this is where we specify what type of default fluid we're going to be working with, or gas. In this case, it is just air. I don't know whether this is going to be a laminar or turbulent flow, so I'm just going to say laminar and turbulent. If you do know, you can actually select or specify either one. This just speeds up the analysis a little bit, but again, if you don't know, might as well just set it to laminar and turbulent. Next, I just have an adiabatic wall. I'm not going to consider any type of wall roughness, although if you do know this type of values, it might be good to set up, because again, it can change your velocity or pressure in your or the pressure buildup in your system. And here's where I set up my thermodynamics parameters and velocity parameters, basically my initial conditions for this analysis. The pressure is going to be atmospheric pressure 101,325, and I'm going to leave the temperature at 68.09. That's the default temperature, room temperature. It's close to 70, but that's I think we're in good shape here. For the velocity, I'm actually not going to set any velocity right now. I'm actually going to set the velocity. I'm actually not going to set the velocity. I'm going to try to gather velocity results based on the rotation of my fan. So however that air is being sucked in and pushed out of that fan, and that is the velocity that I'm going to capture as it comes out. And for turbulence parameter, I'm just going to leave this with the default conditions, and it's going to be set to 2%. I'll hit finish here, and that's it. That is your analysis, that is your analysis pre-setup, which will give you this your design study tree, where you can then go ahead and set some set your rotation regions, your boundary condition, and of course your goals of this analysis. So let's go ahead and do that now. So for the rotating region, what we're going to do is we're going to right click and say insert rotating region. Now for this, you actually don't select the blade, you're actually selecting the region in which that air is going to be rotating in. So in this case, it's actually this area right here that's being selected. Okay, so at this point you can actually see if your air is rotating in the right direction. So it is rotating. I do want it to rotate in the clockwise direction, so the arrows are pointing in the right direction. And next is I'm going to set the parameter. Now for this, I did mention earlier that I wanted to be in RPM, but I did not change that angular velocity unit to RPM. I have it at radians per second. Well, that's not a problem because SolidWorks will automatically convert that for me. So if I go back in here, you can see that it will automatically change that 10,000 RPM to radians per second for me. This is the last time that I'm going to look at this value. It's a preset value for me, so it definitely makes your life easier, where SolidWorks makes all that conversion for you. It's a built-in scientific calculator right within SolidWorks itself. Next thing is I'm going to set my boundary conditions. I have two. I have my inlets, as I had mentioned earlier. So this is the area where I'm going to set that inlet. And all this is going to be just a pressure opening at environment pressure. 101,325 and room temperature. And I say okay, and that's it. This is where that air is going to be sucked in to the fan. The next thing I have is an outlet. So I'm going to say insert boundary condition, and I can select that face. Now, as I had mentioned earlier, if you are just running our system, if you just want air to blow right through from atmosphere to atmosphere, and you want to just see what the velocity is, then by all means you can come in here and say environment pressure and say okay. However, now let's say if you're putting a throttling device in the back there, in the back end, and now it's at a higher pressure, you can actually change this. As opposed to leaving it in environment pressure, you can actually change the environment pressure as well. Just add 1,000 here, but for good practice, we are always going to just change that to total pressure. So it is going to be represented as total pressure. And I'm going to just come in here and say plus 1,000 pascals. And you can see now it's 102,325 pascals. And I say okay. So now the pressure at the end is higher than atmosphere. So there is a gauge pressure of 1,000 pascals acting on the air as it's being blown, as it's going to blow out. Okay. So as I had mentioned earlier, I do have a few goals from this analysis. So it's always a good practice to set up goals. Now you don't actually have to set goals for your analysis. You can just run the analysis and see what happens. But setting up goals is always a good practice because of two reasons. Number one is it's quick access to gathering results. When you solve your analysis, you can just go into your goals tab and it will show you all the results of your preset goals. And a second benefit of setting up goals is that in a steady state environment, it will converge based on your goals. So if you're setting up, say, a velocity, if you want to calculate the velocity on that face, when the velocity is converging at some automated set value within SolidWorks itself, the results will end in a steady state environment. So I'm going to say insert a surface goal, and I'm going to actually select that face, and I'm going to say I can say velocity. I'm going to say max velocity and say OK, and that's it. So I've set one goal there, and at this point your analysis is ready to set up. There's a few other things to do for housekeeping such as meshing the model, but we won't really get into that in this example. This is more of just wanting to show you this example. So I've actually pre-ran some analysis, as you can see here. So let's go ahead and take a look at some of our results. So the first analysis I ran for example purposes or just to test the system itself is atmosphere to atmosphere. So there was no back pressure at all. So as you can see here, it was just a total pressure of actually I changed that, was 101,325. And if we take a look at our flow trajectory, which is a great way to look at your analysis as soon as you're done with it. If you want to completely understand how the air is flowing, flow trajectory is a great place to start. So I'll hit show, and you can actually see how that air is being sucked in, and it has a non-uniform flow here, and as it passes through the straightener, it evens out. And if you want to see this closer as how it moves, you can actually see those spheres moving through your system. So this is just atmosphere to atmosphere. Okay. So this the speed or the velocity of this air that's moving here is its real velocity value. So this can be changed into, say, pressure, but it will all still show you the same velocity. Now this is obviously very interesting here, is because it's the same color, but what we can do is we can reset our plot minimum and maximum, and you can kind of see how that changes. So obviously it kind of makes sense. As it's coming in, the pressure goes up, and then as it goes through the straightener, the pressure comes down and right out of your system. Okay. So another great way to look at this analysis is using your cut plots. So I'm going to just hide these flow trajectories, and if we look at this right here, it makes it much clearer. You can see how the air is being sucked in again through the fan, how there's some rotation there, how it flows through the straightener and comes out. And if you want to get a proper color scheme, you might want to set this both to velocity and have the same chart values. You can see now clearly how the velocity is changing as it flows through the system. Okay. So graphically, all this definitely looks very nice, but we want to be able to get real values, right? So what I've done here is, if we come into our point parameter here, I have sketched a line through my system, and all I really did was I just used our sketch tools. I created a center line, and I just dropped some arbitrary points on this line. It's a straight line from the midpoint of the fan until it reaches that location where I'm gathering all the results. And I would just want to see how the velocity changes as it flows through the system. Okay, so let's take a look at that. If I right click this, edit definition, you can see that all those points are selected. So I have 7 points, and I don't really need pressure in this case, and I'm going to say show. Okay, so this shows me all the different velocity. Now this first velocity right here is almost zero. Kind of makes sense, right? If you look at it clearly, that point right in the middle of that fan is a dead zone. So the air blows this way and this way. So that area right there doesn't actually get much air. So if you don't believe me, next time if you see a fan, just try to put your finger right in the middle, right in front of it in the middle, and you'll see there's actually no air in that area. And then as you go into the second location, that velocity goes up, and then as it flows past the straightener and out the system, the velocity is going down. Makes sense. Now if you want to view this in a graphical form, SolidWorks simulation flow is automatically integrated with your Excel, Microsoft Excel. So I'm going to say export to Excel, and it automatically creates this chart for me. I'm just going to create one more column here, and I'm just going to say points 1, 2, 3, 4, 5, 6, and 7. So we'll say insert a line chart. I'm going to say select the data. This is meters per second. For my x values, it's going to be the velocities. No, actually it's going to be the points. And then for the y, I'm going to select the velocity, and I say okay, and there you go. Now you can actually see how the velocity changes as you go through your different points on that line. Very nice representation of your airflow. Okay. All right, so I think we've answered the first two questions. How do we gather our pressure, and how do we also gather our velocity? Now the last question, right? So if you want to put together all these different values and get some CFM chart. So if you're not familiar with this, and if you have ever for some of you who's gone out and bought some fans. So an example here is like Delta Fans is very famous brand for little desktop fans. They always give you this fan P and Q curve chart where it is airflow versus air pressure, which is typically given to you in CFM versus CFM values. So this CFM values can also be represented as velocity. So if you go to like engineering.com, they typically have like an airflow conversion calculator. So if you put in, say, your meters per second here, and I think if we go back to mine, we were looking at, let's say, some average of 30, right? So if we look at 30 meters per second, that circular cylinder was 14 inches. So your CFM value would be 25,252, which then you can graph out that chart. Okay. So I've actually ran a few different analysis. I've ran it at all these different air pressure. This is the pressure gauge values. So 1,000, 500, 1,500, and 2,000. So basically, I added 1,000, to the atmospheric pressure and 1,500 to the atmospheric pressure, and see what the velocity was. And I was able to come up with a very nice representation. So you can see that it looks very similar. So this is my airflow velocity at one location, at that surface location. and this is the change in air pressure. So it, when I set it to 4,000 pressure gauge, 3,000. This was 2,500. This was 2,000, 1,500, 1,000, 500, and this is 0, which is basically atmospheric pressure. Okay. So I hope that this webinar was useful to you, gave you some idea in terms of what the capabilities of SolidWorks flow simulation, in terms of testing your fans or air cooling systems or even water cooling systems. So if you take into account water instead of air and how water flows through your system, you'd be able to get very similar results. So I did mention earlier that I wanted to share with you what else SolidWorks flow simulation has to offer. So for today's example, we looked at internal and external in internal analysis, rotating components. So SolidWorks flow simulation also has the capabilities to run laminar and turbulent flows, heat transfer, compressible non-Newtonian type of fluids as well. So say blood results exchange, and of course transient analysis. There are also add-ons, electronic cooling, and HVAC add-ons. So if you're in this industry, you might be interested in this as well. So right now I'm just going to open the floor to any questions. All right, so it seems like there's no questions at the moment. Hope that's a good thing. So if you do think of a question, feel free to email me. My email is sashi@catdimensions.com. You can also call us 877-223-4255 and ask for me, and we can also talk about anything that you saw today, anything that interests you in flow simulation, or we can also talk about anything else for your design validation needs. And of course, visit our website www.catdimensions.com to see more pre-recorded videos such as this webinar today. All right, so thank you and have a great day.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.